Good. Okay. Okay, welcome back. We'll continue with low latency memory. We were somewhere in the middle of this. So I'm going to fast forward to the place where we left off. So let's see. Remember, we've covered. Oh, what's over here? Okay. Yeah, last thing we covered was low-cost interlinked subarrays. And this tackled the problem of subarrays not being interconnected with each other at high bandwidth. And this enabled movement of roads between subarrays. And it overcame one of the big disadvantages of row clone, as we discussed earlier. And it also enabled other benefits. Now you could actually do caching inside from one subarray into another subarray in DRAM. And you could reduce the pre-charge latency as well. And this was an example of changing the DRAM microarchitecture to reduce latency. This is not sounding good. It's okay with you? Maybe my ear is very sensitive. There's a very high pitch somewhere. I think the fundamental problem is the level of the... yeah. I'm not sure if it's a connection. I mean, if the level of the sound is very high, usually it has that problem. That somehow.
So it's probably not the mic.
Okay.
Okay, if it's worse, we'll switch to the other one.
Is there the other one still here?
I think, yeah.
Okay. Yeah, if we can switch, maybe that's better because this is strictly worse right now. Okay, you can jog your memory with the paper, I guess, while we're trying to turn this off. Okay. Yeah, you think it'll work? Just that?
Yeah, yeah. This is the same one.
Okay. Is this better? At least it doesn't have that high pitch thing. Let's see. And I'm used to it, so I know how to use this better maybe. I don't know if that's true. Okay. Okay, is this better? I think so, right? Yeah. Okay, good. Okay, so we were actually looking at the first reason for the long latency, and that's really the design of the DRAM microarchitecture. People have not really thought of designing the DRAM microarchitecture to be low latency to begin with, because their focus was really high capacity. And even though there are examples of DRAM microarchitecture that are low latency, they come at very high cost. So I think a very important research area going forward is how do we design memories and DRAM to be low latency at not a lot of cost. And I think these two ideas that I mentioned gave you tiered latency DRAM and LISA are examples of that, and there should be more going forward. So let me give you the second reason where we're wasting latency, and I think this may be even easier to, some of the ideas that we're going to cover may be easier to adopt relatively quickly. And the second reason is the one-size-fits-all approach that we have to latency specification today in DRAM. Basically, we're using a single set of latency or timing parameters that doesn't change even if the temperature changes. That doesn't change based on the chip. That doesn't change based on the row or parts of a DRAM chip. That doesn't change based on supply voltage levels or application data. I call this the fixed latency mindset. It's really there because we're specifying things that way. But that's not the case in real life. Basically, if you look at the reliable operation latency of a memory chip, it's very heterogeneous. Heterogeneous in terms of space as well as environmental conditions and across different chips, across temperatures, chips, parts of a chip, across different voltage levels. So our dream, if you will, was to find out and use the lowest latency one can reliably access a memory location with. You could do this at different granularities, at the chip granularity, at the module granularity, at the different parts of a chip granularity. And we wanted to do this dynamically. Ideally, you would like to do this dynamically. But I'm going to start with a mechanism that doesn't even do it dynamically. And we're going to talk about adaptive latency DRAM. The key idea is very simple. Based on the temperature and the DRAM chip, use a second set of latency parameters. So specify two latency parameters, one at high temperature, one at low temperature, for a given DRAM chip, and switch between them depending on the temperature.
It's on a chip level? What granularity?
You could do it at the module level, certainly, yes. basically we're exploiting heterogeneity and latency because of temperature as well as module-to-module reliable operation latency heterogeneity. And then this is basically static. Somebody specifies these parameters. And then we're going to look at different approaches, flexible latency DRAM that looks at heterogeneity inside a chip or inside a module. And then we're going to try to analyze the causes of the latency variation inside a module and look at why there's systematic variation in latency and try to come up with methods for dynamically figuring out the lowest latency one can access a chip with. And then we're going to talk about voltage-latency relationship. We're going to switch to voltage. And then we actually are going to talk about what else can you enable if you actually change the latencies in a way, in a controllable way. And I'm actually going to talk about one of the most recent works that was presented yesterday at ICCD. I have some slides on that also. That basically builds on this flexible latency DRAM. Okay, does that sound like a good plan? At least that's for the first part of the morning. Basically, we would like to find sources of latency heterogeneity and exploit them to minimize latency. In the previous one, we were actually creating heterogeneity. In tiered latency DRAM, we were actually architecting heterogeneity into the system by segmenting the bit lines. Here, there's heterogeneity that exists, and we're going to try to exploit that. So why does that heterogeneity exist? So this is an example. You have low latency. This is the reliable operation latency. It's low here, it's high here, and depending on the manufacturing variation, some chips or modules can operate at low latency reliably. Some modules cannot. So they have to be operated at high latency. So you really have latency variation. And even within a chip, you have that variation. So even within a chip, you have slow cells and fast cells. And we're going to talk about why that's the case. Maybe obvious. I mean, some of them are large cells. Some of them have large charge. As a result, they can be faster. So as I said, DRAM latency is the delay as specified in the DRAM standards. This doesn't reflect the true DRAM device latency. Because of imperfect manufacturing process, you have latency variation. And as a result, you get a picture like this between different chips. And within a chip, you have a variation also. And what industry does today is they choose a high standard latency to increase the yield as much as possible. And if you choose it over here, then all of the chips are acceptable to operate at that very high latency. And that's essentially what's done today. But that may not be the best way. So what causes the long memory latency? One cause is really the conservative timing margins. And if you look over here, this is really a timing margin. This chip can operate perfectly at this, and we're putting a huge margin on this chip. And it's very conservative. And DRAM timing parameters are set to cover the worst case chip at worst case temperature. I didn't even show that temperature dimension in that before. Worst case temperatures, basically chips are specified to cover 85 degrees. But common case is not necessarily 85 degrees operation. In fact, in some cases, you can operate at much lower degrees. But this enables a wide range of operating conditions if you choose the worst case latency that you have to use at worst case temperature. And you want to cover the worst case devices, basically, this means that DRAM cell with the smallest charge across any acceptable device, you're setting the latency based on that. And you want to tolerate process variation at acceptable yield. And yield is usually very conservative, right? You don't want to use much yield because that directly affects your cost. As a result, this leads to large timing margins for the common case. Common case may be an average case device that's somewhere here in the distribution as opposed to here, and maybe average temperature. Of course, temperature varies widely depending on the devices that you have, but in some devices, the temperature is relatively low. Okay, so basically, you want to understand and exploit variation in DRAM latency. So I'm going to go through the basics very quickly again. This is how DRAM operates. As you know, there are 3 steps of charge movement. That's activation. Activation enables sensing over here. And then you need to restore the charge. After the sense amplifier gets enabled, it restores the charge back. And you need to pre-charge the array. You know this very well by now. And let's take a look at what happens to DRAM charge over time in these 3 steps. This is initially cell is charged. This is the sense amplifier VDD over 2, as you can see. Initially, this is the charge level of both, assuming that the cell is charged. And when you activate the cell, you start sensing. And at some point, sense amplifier kicks in and starts driving and restoring the charge. And once the charge is restored in the cell, in theory, that happens at this point in time. But in practice, we wait until here. So that's the difference. Basically, we add some margin to this. Basically, even though the cell restoration may be done at this point, the timing parameter is specified to have this very long margin over here. So this is the timing parameter. So why does DRAM need the extra timing margin? In addition to being conservative, there's variation, right? And this variation makes manufacturers in general conservative. So you have process variation and temperature dependence. We're going to look at both. Process variation means that DRAM cells are not equal within a chip or across chips. And this leads to extra timing margin for a cell that can store a large amount of charge. Even if you don't have any margin for the cell that has very little charge, this leads to margin for every other cell that is basically stronger. So I'll pictorial show this. Ideally, you get same size, same charge, and same latency. And ideally, you don't add any margin to it. But there's margin added to that also. But in reality, you have cells that look like this. Of course, it's a pictorial, right? Some cells are bigger, some cells are smaller. Some cells are basically stronger and weaker in terms of the charge drive they have. You have different size, different charge, different latency. And because of this large variation in cell size, you get a large variation in charge in the charge drive as well, as a result, large variation in access latency. So let's take a look at where the process variation comes from. Basically, this is how you access the DRAM through the access transistor. You have cell capacitance, certainly, and variation affects the capacitance of a DRAM cell, directly affects the charge as a result. The contact resistance, there's variation over there. That directly affects how fast you can access the charge. And there's also the transistor performance, and there's variation over there, and that also directly affects how fast you can access. So it's not just the capacitor, it's really a combination of all of these factors that lead to slow or fast cells inherently. So I'll call these small cells. Small meaning they're basically defective in terms of either at least one of these or all of these, right? So you have small cell capacitance, high contact resistance, and slow access transistor. You can think of that's the worst case cell, right? And these exist because you cannot control the manufacturing perfectly, right? And as a result, you need to have high access latencies to such cells. You don't want to get these cells wrong. You need to wait long enough such that these cells are read correctly. Okay. Okay, it's back. Maybe there's a row hammer attack on my computer. Okay. So the second is temperature dependence. DRAM leaks, I mean, we've said this before, right? As each cell leaks more charge at higher temperature, and it's an exponential relationship with temperature. As temperature increases, you leak exponentially faster. And this leads to extra margin for cells that operate at low temperature. If you're operating things at low temperature, and if you specify the latency for operation at high temperature, you're really assuming that charge leakage is faster, which means that you have little charge to begin with. But that's not true at low temperatures. Basically, this is a pictorial way of looking at it. At room temperature, you have this. At hot temperature, you have this. At room temperature, you have small leakage. Here, you have large leakage. And cells store small charge at high temperature because they leaked a lot to begin with, and large charge at room temperature because they're much cooler over here, which means that because they're much cooler, they have more charge, they can drive things much faster. Whereas here, that's not the case. So as a result, you get large variation in access latency across temperatures, which means across time. Right. Okay, so the problem is DRAM timing parameters don't take into account any of this variation. They basically are dictated by the worst case plus margin on top of that worst case. What is the worst case? The small cell with the smallest charge in all acceptable DRAM products, and that are operating at the highest specified acceptable temperature. And this leads to a large timing margin for the common case. And our idea was basically very simple. Once you have these observations, the idea is really easy. You optimize DRAM timing for the common case, for the current temperature, current DRAM module. So why would this reduce latency? Because, as I said, a DRAM cell can store much more charge in the common case, if you have a low temperature, strong cell, than in the worst case. And more charge in a DRAM cell leads to faster sensing, faster charge restoration, and faster pre-charging. Everything becomes faster. And as a result, faster access, clearly. Okay, so this is actually how the three parts are accelerated. I'm going to cover each of them with some experimental results also. You can sense cells with extra charge faster, lower sensing latency. There's no need to fully restore cells with extra charge, lower restoration latency, because they already almost are restored. And there's no need to fully pre-charge bit lines for cells with extra charge because they're almost there. You get the lower pre-charge latency. So we've actually characterized this with our real DRAM infrastructure. As I said, you've seen this picture many times also. And you can do these studies yourself also. You can repeat and figure out on your own. Basically, let's look at the faster sensing part. This is the typical DIMM at low temperature. It has more charge. There's strong charge flow because of that more charge. As a result, you sense faster, right? And we've characterized almost 1,000 chips, basically 115 DIMMs in this case. And we've shown that if you reduce the TRCD, the activation latency, by about 17%, you get no errors at 55 degrees Celsius. So what is low temperature? It's 55 degrees Celsius when we're operating it. We cannot perfectly control the temperature also, but I'm going to show you real results from real systems that we operated for more than 3 months where you don't get any errors when you reduce the latency. Okay, so basically, at low temperature, you have more charge, so you have faster sensing, and this is empirically supported in real devices. The second one is reducing the restore time. This is interesting because this led to a lot of other work that basically led to partial restoration of the charges, of the charge in DRAM cells, reducing the latency even more. But basically, again, at low temperature, you have less leakage, meaning that you have extra charge, meaning that you don't need to fully restore the charge over here for many cells, because you have enough charge to sense it afterwards, right? So that's the idea of partial restoration, not full restoration. And there are other works that built on this. You can see actually tens of works, I think, in this area right now. We have one that's upcoming at Micro that I'm going to very briefly mention. But basically, this way you can reduce TRAS and also write latency, write recovery, by significant amounts, 37%, 54%. And this is average, actually. There's a distribution across the modules, but I've given you the average across the modules that we've tested. And you get no errors, again. Basically, you can reduce the reduction of the time. Oh, it's back. Okay. Am I doing something to cause this? I'm not sure. Okay. You basically restore the charge to a smaller level because you already have more charge to begin with at 55 degrees Celsius. Right? Maybe you don't want to do this at 85 degrees Celsius because you don't have a lot of margin in restoration time. Okay. So you can do the same thing for pre-charge. I didn't put it over here, but the third observation is you can reduce the pre-charge time with a very similar observation. Okay, the key idea of AL-DRAM is very simple. Optimize DRAM timing parameters online. There are two components of it. Somebody provides multiple sets of reliable DRAM timing parameters at different temperatures for each DIMM. In the simplest incarnation of this, you don't even do it for each DIMM. You do it across all of the DIMMs, maybe, but you specify two global timing parameter, sets of timing parameters, one at 85 degrees Celsius, just like today, and another one at, let's say, 55 degrees Celsius. That's the easiest path for implementation. But if you do it for each DIMM, of course, there's a lot of variation across the DIMMs. As a result, you gain even more. And system monitors DRAM temperature and uses appropriate DRAM timing parameters for the DIMM in question. So how do you monitor DRAM temperature? This actually already exists. And as long as you did it at coarse grain, this is not bad. And a lot of the DRAM temperature sensors are actually fine-grained enough to cover two different widely varying sets of latencies, sets of temperatures. Yes? So I think if the temperature changes really fast, there might be. You need to detect it quickly, but temperature usually doesn't change extremely fast.
No, like in the protocol, the DDR.
No.
Like changing from one timing parameter to the other because you.
No, I mean, you just need to ensure that the existing stuff is serviced, basically. But there's no issue. That's very, very little. You can easily change the timing parameters, assuming you design the memory controller to be that way. Basically, you need to wait until the previous accesses are coming back. But I think if there are issues, you can also handle that, right? You can wait even longer, right? If you figure out there's an emergency in the memory controller, you could also wait a little bit longer. So I think the design should not be impacted by this almost at all. Yes?
In the previous slide, you said that the numbers are average. Yet you said no error. I'm not sure that employed. It's average, so how come no error?
Yeah, basically, I give you the average latency reduction numbers, but we don't see any errors. But there's a distribution of course, right? Some of them you reduce the latency by 10%, some of them you reduce the latency by 90%, let's say. We get no errors in those cases. But if you average all of those latency reductions, you get 50%.
But you must get the lowest reduction in order to get no error anyway.
Yeah, but I'm suggesting that you do it for each DIMM. Basically, you specify the latencies for each DIMM.
The refresh rate has not anything to do with it. I mean,
Yeah, we're not changing the refresh rate at all here.
Okay.
That's right. Although the refresh rate is actually, there's temperature compensated refresh in systems today. So refresh rate already adapts to the temperature today. At 64 milliseconds, every 64 milliseconds at low temperatures.
Forget the idle time of refresh. Can I get the similar phenomena by reducing the refresh? Then the latency will go down also?
Oh, refresh latency, you mean?
Yeah.
Yeah, you could actually do.
The refresh, the time between refresh, I mean, the charge goes down until
Yes.
the next refresh, okay?
That's right.
So if I reduce the time between the refresh, then the charge will still be high enough to get a lower latency DRAM, or I need something completely.
Well, I guess if you just refresh the cell, you have a lot of charge.
Yeah, that's what
And that actually, you can exploit that also. I'm going to talk about that.
Okay.
So that's another way of having more charge in the cell. If you know when you've just recently accessed or refreshed the cell, you can actually reduce the access latency. And that's another idea that I'm going to talk about. But here, I'm not even saying that. I'm not even exploiting that. You're talking about a different variation, time from the last refresh or time from the last access.
To understand the relation between. No?
Sure. Okay, yes.
I just wonder if aging has impact on these parameters or relatively it is fixed.
Yeah, so that's a great question. That's something we didn't test over here, but that's why we developed more dynamic methods later on that will cover aging effects also. But that's a great question, I think. And we're always interested in whether aging, how much aging affects. So even in this case, we're adding extra margin to cover for aging. So that's the reason to add the extra margin, really. Yes? Well, each DIMM, that's a good question. I think the testing cost is the harder part over here. But I think it's good to test every DIMM anyway. Somebody will be doing that, in my opinion. It could be the buyer today, because they want to have some quality assurance.
The question is, do you know how much the yield would be in each time,
Yeah.
in each group?
Exactly. So that's a good question.
Group, or
Yeah, I'm not sure at this point. I think those things are. I mean, yield is a very difficult question to answer academically. But I mean, that's the as we will cover in the idea advantage and disadvantage. That's the disadvantage of the idea, basically. That's why we want to actually develop online methods for figuring out the latency. That reduces the testing burden from the manufacturer. And if you do it online testing anyway for other reasons, you can actually discover this latency much better. Very good question. Yes. Yes. Yeah, exactly. I agree, I think.
Is it possible to do something like Razo where you can check whether the latency, you obey the latency
Yes.
and adapt it better even? Or?
Yeah, basically it's like what we've discussed in Avatar, right? You reduce the refresh rate and you see if there are errors using the error correction circuitry, and then you pull it back. You could play similar tricks over here also, certainly. Yeah, certainly you could do those. I think these are all good ideas. Well, I think once you change the mindset from fixed latency, there are a lot of ideas to explore. I think the most difficult part is changing the mindset from fixed latency to, oh, I have actually very heterogeneous latency, and I can do whatever I want in my memory controller to get that heterogeneous latency. Okay, so okay, the key is who specifies these reliable timing parameters, and there are issues associated with this. In this case, assuming that somebody specifies these reliably, I believe DRAM manufacturer can do it. Then let's see what happens. So we've actually done DRAM temperature measurements. We've seen DRAM standard optimized for 85 degrees Celsius. We've seen temperatures that are like this, relatively low. And we don't see errors, actually, even if we make our systems really loaded. These are a different issue, of course. The temperatures are maybe much higher over here. And also, there are other previous works that I've shown that DRAM temperature is low, and people want to keep it low for other reasons, like refresh is an example. Yeah. Okay. So in the common case, I will posit that DRAM operates at low temperatures, certainly not at the highest temperatures. And remember, the relationship is exponential. Right? The charge, you have exponentially more charge as you reduce the temperature. So this is the latency reduction summary for 115 DIMMs that we have. Basically, if you aggregate things, we can reduce the read latency by about 32% and write latency by about 55%. Again, this is average. There's a distribution across the DIMMs. If you really want to specify only one latency, you need to take the lowest one, as you mentioned earlier. And this is the for each timing parameter. You can read the paper. And actually, all of the data that we have is available online. You can go and browse all of every single DIMM that we've tested over here. So we actually wanted to get the potential benefits that you might get with this using a real system. And in some real systems, you can actually change the timing parameters in the memory controllers. And a lot of gamers actually use this, except they don't necessarily they don't necessarily care about the reliability of their system. They just change it, and they hope that it works, right? And sometimes they get errors. Okay, they're annoyed at that point, and then they back off. So it's like having an ECC at the human level, right? You're the error correcting logic, and you back off a little bit after that. The problem is you cannot dynamically do this, at least in this system that we have. So we had to do it statically, and we basically wanted to ensure that the system is operating lower than 55 degrees Celsius. We didn't ensure that, but the system operated lower than 55 degrees Celsius without us doing anything. And we tested 35 workloads. Some of them are quite intensive. GUPS is very random access, for example, for more than 3 months with the timing parameters that we figured out for the DIMM that we tested at 55 degrees Celsius, so with lower timing parameters. And if you do that with one of the given DIMMs, we've done it for many DIMMs, of course, but this is one example DIMM. The workloads don't get any errors over the course of months, but you can actually improve performance. This is a single core performance. The average improvement is about, for the memory-intensive workloads, which are the more interesting ones, it's about 6.7%. And this is real improvement on a real system. And if you actually are more memory-intensive, how do you get more memory-intensive? Basically, we replicated these workloads and ran them together on the 4 cores that we had. And the performance improvement that you get, of course, increases. Basically, on memory-intensive multi-programmed workloads, you get about 14%. And again, no errors over the course of many, many months. I think this shows 2 things. One is you get actually latency reduction that translates into performance. And the second is the memory is actually operating at low temperature, even without us controlling it. Because if we actually, we didn't really implement the dynamic mechanism, right? There's no way we could implement the dynamic mechanism on a real system because we cannot dynamically change the timing parameters in the controllers that we had, at least. We didn't have that sort of programmability into that real system's memory controller. We just hope that it actually operated at low temperatures, and that's exactly what happened. Okay, so there's also more evaluation in this work. Basically, this is somewhat preliminary evaluation, but reducing latency is good for many things. It's good for energy also. AL-DRAM reduces DRAM power consumption by about 5.8%, and the major reason is reduction in row activation time. But basically, you're driving these interconnects for much shorter time periods. As a result, you're reducing the energy. Okay, let's talk about advantages and disadvantages, although we've covered some of them maybe. So it's a simple mechanism to reduce latency. I think it's not that hard to adopt except for the testing cost potentially. It gives you significant system performance and energy benefits, and benefits are higher at low temperature. So this is another reason to operate things at low temperature. And low cost and low complexity. It doesn't add much complexity. The disadvantage is basically this. We need to determine reliable operating latencies for different temperatures and different DIMMs. And that gives you a higher testing cost. And somebody needs to do that. And that's essentially, this might not be that difficult for low temperatures, but might be difficult for every single DIMM. And that's what motivated us to actually look at how to actually achieve something like this with more dynamic methods. And if you're interested, this is the paper. And all of the data is actually online on our website. So before I go into dynamic, question? Okay. Before I go into dynamic methods, let's look at the latency variation in a different way. AL-DRAM exploits latency variation across time. meaning different temperatures, and across chips. Is there also latency variation within a chip? That's the next question that we asked, meaning across different parts of a DRAM chip. And that's what we essentially found. Basically, this is results from 7,500 rounds of testing over 240 chips. And this is the TRCD, which is the activation latency, and this is the bit error rate that you get. This is specified standard latency is 13.1 nanoseconds. And as you can see over here, we don't get any errors until we go down to 7.5 nanoseconds over here. And once we get to 7.5 nanoseconds, some chips fail a lot. Some chips don't fail a lot. Once you go to 5 nanoseconds for the activation latency, a lot of chips start failing a lot. And if you actually reduce it to 2.5, a lot of basically pretty much all of the chips fail over here. That's a very high bit error rate. It's about 1 out of 100, right? So clearly, this I've shown you earlier, but I just wanted to show this again. There is different characteristics across different DIMMs, very wide variance at 7.5 nanoseconds over here. Some of them have very few errors, some of them have many errors over here. And this, as you reduce the latency a lot, it's rife with errors over here. Yes?
Do you distinguish between failure in read and write? Because in read, because you have the ECC, not always you care about errors. On write, you do care.
Yeah. So in this case, we don't use ECC. These are non-ECC chips, but we don't distinguish them, right? But I think that's a good idea to look at, to go into more finer grain characterization of the errors.
Maybe in some cases you don't care about errors.
Yeah, maybe. Yeah, it's possible actually.
Usually
I think
you have error like it's 1 bit in a row, or
it can be more. Yeah, it can be more. I mean, especially over here, it can be more. If you're at lower, it's actually usually 1 bit per row.
ECC is enough, no?
It depends. I think if it's 1 bit, sure, but if it's not 1 bit, basically, I think it really depends on your operating regime, right? Okay, so this is the spatial locality of activation errors from one DIMM. This is the cache line, and these are the different rows. And we're looking at TRCD equals 7.5 nanoseconds. As you can see over here, errors are very clustered. So ECC may not be enough, actually, in this case. Activation errors are concentrated at certain columns of cells. And we're going to go back to this, actually. It turns out these are very column-based. It seems like there are some bit lines, for some reason, are not as reliable as some other bit lines. We don't know exactly why this is happening, but there's certainly some variation across different columns. So ECC might work if you actually get errors only in one column, right? Okay, so that's one example. And we've seen this many, many times. That's why I put this over here. And the y-axis over here is the probability of cache line with greater than or equal to 1 bit error over here. Okay. So once you have this observation, the observation that DRAM timing errors, meaning slow DRAM cells, are concentrated on certain regions, you can take advantage of this somehow, right? Basically, the idea is to have a software transparent design that reduces latency. The key idea is to divide memory regions into regions of different latencies. And the memory controller uses lower latency for regions without slow cells and higher latency for every other region. Then the key question is, how big are these regions, right? I mean, hopefully this figure should show you that the lower latency regions are most of it, and the regions that you require higher latency for should be a very small fraction. And that's exactly what we see. So this is, we're going to look at some configurations over here. Basically, this is the fraction of cells, and fraction of cells that can reliably operate with different TRCDs and TRPs. And these are profiles of 3 real DIMMs, and we have all the results online also, but I picked 3 over here. So if you look over here, this is the baseline. 100% of the cells operate correctly at 13 nanoseconds. This is one of the DIMMs. Most of the cells operate correctly at 10 nanoseconds, and a small fraction can operate at 7.5 nanoseconds. But if you look over here, D3, most of the cells can operate correctly if you reduce the latency to 7.5 nanoseconds. There is a very small fraction that requires 10 nanoseconds to operate correctly. So there's clearly significant variation across the DIMMs, but also within the DIMM. Right here, for example, you can access 99% of the cells with 7.5 nanosecond latency and only 1% of the cells with a much smaller latency. Yeah, so that's a good question. There is some contiguity. I mean, we don't have the full analysis of this, but as you can see, there is some contiguity over here. These are different columns, and sometimes columns are coupled with each other. They're not completely randomly spread, I will say. Okay, so this is basically the fraction as you can see. And the TRP is very similar as over here.
So everything here work on 10 nanoseconds can work.
Exactly, yeah. As I showed earlier, everything, because of the temperature, basically, everything works at 10 nanoseconds. And this is the upper bound, of course. Upper bound, everything works at 7.5 nanoseconds. Right? We're going to compare to this upper bound using simulation. So if you actually have a mechanism that keeps track of which cells have to be operated at low latency and which, so basically you have two regions in a given DRAM DIMM. Some regions can operate at low latency and some regions can operate at high latency. And you encode them somehow. It could be Bloom filters. We didn't go into a lot of implementation detail in this work, but you could encode them using Bloom filters, for example, similar to what we've discussed earlier, and use low latency for the region that doesn't require high latency and use high latency for the regions that require high latency. Now, if you do that in the memory controller, these are the benefits that you would get. I don't know what happened here. This is supposed to reach 1 over here, but somehow PowerPoint doesn't like that to be aligned. But essentially, this is the baseline across 40 workloads. This DIMM that has this sort of profile, even in that DIMM, you gain about 13% performance. In this other DIMM, you get about 17% performance. In this other DIMM, you get about 19.5% performance. And the upper bound is, in these workloads, 19.7 if you operate everything at 7.5 nanoseconds. So you get very close to the upper bound for some DIMMs that, where the profile is such that most of the cells are actually low latency. But of course, this is now a more complicated mechanism, right? The implementation is not as easy in the memory controller. And also, you need to do much heavier profiling to figure out which part of the DRAM chip can you operate at low latency or high latency. And we've actually been developing profiling methods for that as well. And I believe a static profile will work, and that's we're going to look at that when we talk about our ICCD paper that was presented yesterday.
What it means for the memory controller?
Yeah.
It allocates addresses differently?
Basically, the way I like thinking about it is whenever you have an address to access, you need to decide what latency timing parameters to use, right? Which means that you need to consult a mapping table that tells you use the low latency parameters or the high latency parameters. Yeah.
It's reactive action according to the address. It's not like you try to optimize
Exactly.
accesses to
Exactly. Yeah. So the latency of the table, I think that's not going to be very large, but you can overlap it because there's queuing that happens in the memory controller, and you can overlap it with everything else that goes in the memory controller. It's more throughput, and it's also the size of the design of the table, basically. Today, this sort of thing doesn't exist, right? Based on the address, you don't look up the latencies, as far as I know. There are memory control experts here that can correct me if I'm wrong. But as far as I know, you don't do that. It's very similar to Radar, right? Based on the address, you look up whether you need to.
Yeah, but also has to be an SRAM lookup. Otherwise, you have double latency.
Yeah.
Lookup and
Yeah, but I think that lookup can be overlapped with many other things that goes on in the memory controller.
again, it's not latency if someone is waiting.
Mm-hmm. Yeah.
If you're queued anyhow, latency of the actual lookup is not the major thing.
That's right, exactly. Yeah. Okay. Okay, basically the key takeaway is you can improve performance by exploiting spatial latency variation within DRAM. I think there's more to do in this area to make these implementable. So advantages, you get even more latency reduction beyond adaptive latency DRAM by exploiting within-chip latency variation. The disadvantage is even higher testing cost, as you can see, and more complexity. I say slightly over here, so it really depends. And this is the paper that describes a lot of what I just said. Okay, after that, I think I go to this one over here. Basically, we were really interested in other characteristics. How are activation failures spatially distributed in DRAM? This is not a really nice graph over here, but it turns out it's at the subarray level. At different subarrays, you have different columns that are vulnerable, if you will, at low latencies. So you really need to keep track of things at a subarray level. And we can discuss it in more detail. And the reason is basically bit line. You seem to have problems with the bit lines, and some bit lines are stronger. Actually, many bit lines are strong over here. This latency over here is very low. That's why you see these shades of grays over here. But if you actually pull the latency to be a little bit higher, you see only a few columns that are failing. So basically, you have these errors localized to the columns, and if you need to identify these columns, which means that you can actually do some remapping. Okay, that's the key takeaway over here. Activation failures are highly constrained to local bit lines. So the other question that we had is, if assuming you profiled, yes?
I just wonder, is there any correlation between the graph that you showed previously in Rollhammer?
Mm-hmm.
Is there any connection between all this
I see.
stability or
That's a good question. I wouldn't expect that correlation, but we didn't do that study either. So
it can be very interesting
Yeah.
to see because if
Mhm.
they have some correlation, then it has a huge impact on security.
yeah, maybe. I think it'd be good to understand all of these different correlations between different types of failures in DRAM. I agree with that, I think, general statement. But in this case, I'm not sure if I would expect that type of correlation between the columns and the rows. But maybe that with the other latency failures, there could be correlation. Okay, so the other question that we had was, what is the variation in terms of latency? If you, let's say you said, okay, I can reliably access the cell with this latency. Is that going to be true in the next minute, in the next minute, next minute, next minute, and next day, let's say? Of course, we cannot test it for 5 years, probably. This is not going to take into account the aging effects. That's why we call it short-term variation. And it turns out this doesn't change significantly. This is the failure probability at time t1, and this is the failure probability at time t2. And we have different t1, t2 combinations over here, tested over many chips. I think more than 200 chips, again, LPDDR4 here. Basically, there's a very strong correlation between the failure probabilities that you get. Basically, the key conclusion is that a weak bit line is likely to remain weak, and a strong bit line is likely to remain strong over time. Not 5 years, but certainly months. Okay, so the key takeaway is we can rely on a static profile of weak bit lines to determine whether an access will cause failures. Of course, you need to add margin on top of that for aging and other types of variations that you cannot control. So the other observation is write operations. This is something that's really interesting. This is in our ICCD paper this year. How are write operations affected by reduced TRCD? If you look at, you have some weak bit lines over here. Doesn't matter. You activate an entire row, which brings the data into the local row buffer. If you're actually doing a write to that location now, you don't really need to wait for the entire activation latency at that point. You can actually start the write into the sense amplifier, and you will have enough time to actually drive the charge. So write operations are not really affected much if you reduce the TRCD significantly. That was our observation. Because you're driving with new data values into here anyway. And while you're driving new data values over here, the sensing is happening over here anyway. So you don't really need to wait for TRCD for the write operation that's happening. TRCD is happening anyway while you're doing the write, basically, for the rest of the row buffer. That's the idea. So it turns out you can reliably reduce issue write operations with significantly reduced TRCD. And we saw that in our devices, it's about 77%. That's a lot of reduction for write operations. But of course, this is limited to writes. You cannot do this for reads, because reads, you really need to get the data over here to be able to read it. Whereas writes, the data is coming from the outside. Okay, so that's the proposal over here. We use a static profile of weak subarray columns. We identify subarray columns as weak or strong, and we assume that the one-time profiling step plus some margin is good. There are 3 components to this idea. One is variable latency cache lines. I'm going to explain it. And the other is reordered subarray columns based on some other observation. And the last one is the simplest one, which is reduced latency for writes. For all writes, you reduce the TRCD. Let's look at the first one over here, VLC. Basically, you identify cache lines comprised of strong bit lines. Some of them are weak bit lines over here. Some of them are strong bit lines. And access the cache lines that map to the strong bit lines with a reduced TRCD. That's the basic idea over here. Whereas if you're trying to access a cache line, basically activate a row, and then the first access is going to that cache line that's at a weak bit line, you cannot use a reduced TRCD for that because that's weak. But if you're activating something and it's a strong bit line, you can use a reduced TRCD for that. That's the idea. So it's very simple. The second one is a little bit more complicated, but the observation is that you have cache line 0 and cache line 1, and you can remap cache lines across DRAM at the memory control level so that cache line 0 will likely map to a strong cache line. So what does this mean? Cache line 0, it turns out that we found out in real applications, you normally access cache line 0 first because you're streaming. So the first thing you access in your row is cache line 0. But your cache line 0 is usually mapped from the left to the right, if you assume that you're doing the mapping from the left to the right over here. But you may have actually a weak bit line over here. So if you're accessing cache line 0 the most, map it to a strong portion of your subarray, of the bit lines, such that the first cache line that you're likely to access is going to be in the strong portion. As a result, you have a reduced latency. That's the idea. It's empirical observation. Most of the time, actually, I think about 22% of the time, you access cache line 0, even though you may have 128 different cache lines in your row. Okay, the last one is, as I said, very simple. It's the simplest one, perhaps. All bit lines are strong when issuing writes. There's no weak bit line in a sense. So you write to all locations in DRAM with a significantly reduced TRCD. Basically, for all writes, you reduce the TRCD. I think this is kind of obvious in hindsight. It's amazing that it's not done yet, but I think it will be done. Okay, so that's the most recent work that was presented yesterday by Jeremy. Any questions, thoughts? Yes? Okay. Okay, then let's move on and talk about something else that we explored along the way. We have a lot of spatial latency variation within a chip, and we wanted to ask the question, why is there spatial latency variation within a chip? Yes?
Could you reiterate why is writing always considered as a strong line?
Basically, whenever you're doing a write, you don't need to wait until all of this thing. Basically, you don't need the cache line that you're to be read from the row buffer, right? What you're doing with TRCD means that wait until the cache line that you're actually accessing is amplified over here. But you don't need that data. You're supplying the value from somewhere outside. So there's no reason to wait for TRCD before you start the write. That's the idea. With reads, it makes a lot of sense to wait because you need that data. With writes, you don't need that. You don't need that. Okay. And if you want to learn more, this paper has more detail. Okay, so why is there spatial latency variation within a chip? And we've actually verified this. This is actually real results across, I think, more than 200 chips. You can really reduce it by 77%. And we wanted to reduce it even more, but now you start getting errors because you probably have a lot of noise over here in the sense amplifier. Okay. Okay, so I'm not going to answer every possible spatial latency variation, but there's some systematic spatial latency variation that you have within a chip that we're going to look into. And that's really caused by how close a cell is to the sensing structures. So if you look at this picture over here, and the paper has actually much nicer pictures with many, many subarrays. We just aren't able to fit them over here. But if you look at one subarray, it'll give you the basic idea. If you look at across the row, some cells are closer to the sense amplifiers, some cells are farther away from the sense amplifiers. If you're closer to the sense amplifiers, you're naturally faster because you're driven much more quickly, right? If you're farther away, you're driven much more slowly. So there's inherent variation because of that distance. If you're closer to the word line driver across the columns, you're faster because basically word line is activating you first, intuitively. Whereas if you're farther away from the word line driver, you're slower, naturally. So clearly, you have a natural latency variation within a subarray. There's an inherently fast region that's close to sense amplifiers as well as the word line drivers. And there is an inherently slow region that's over here. And this leads to a systematic variation in cell access times because of the physical organization of DRAM. And we wanted to exploit this, basically. And the key idea that we're going to try to exploit is, if you actually know what region this is, then you can profile only that part dynamically and say, figure out the lowest latency at which you can operate this one. And by nature, or by induction, that latency will be good for everything else. Because
you say that columns that are some columns
yes,
that are-
that's right, yes. So that's true, yes. But we're going to, that's why I'm not going to explain everything over here. So there is, I'm going to handle that in a different way. So this is called design-induced variation aware DRAM, or DIVA-DRAM. There's an inherently slow region. Profile only those slow regions to determine the minimum latency somehow. And this is dynamic and low-cost latency optimization. Now, this is good. There's an inherently slow region that's caused by design-induced variation. It's a localized error, but that doesn't work for everything, as you mentioned. There's also some stuff that is slow inherently, not because of design-induced variation, not because of systematic variation, but because of process variation. I believe bit lines are an example of this, actually. That's why you have these localized errors in the bit lines. So you have these random errors. And the idea in this work that we had was you profile and figure out the latency based on this, and for these random errors, you rely on ECC, error correcting codes. Error correcting codes are very good at doing correcting these errors if you reduce the latency for these. And you can find these with online profiling. The key question is, how do you figure out that region? Well, that's the tough part. You need to reverse engineer your DRAM, or somebody provides that to you. And I believe DRAM manufacturers should be more open to the memory controller. If they are, then memory controllers can figure this out relatively easily. So basically, that's the idea. You combine error correcting codes and online profiling. And this way, we can reliably reduce DRAM latency. We don't need to rely on somebody providing that latency. It's very similar to what you said earlier. If you get errors, maybe you can back off the latency also. And that's, you combine this with your profiling as well. So that's the idea. And the paper has more detail as to how you do this profiling. I'm not going to go into that and bore you. But these are the latency reductions that you get with a different set of, a newer set of DRAM chips that we've examined. So AL-DRAM, adaptive latency DRAM, for example, at 55 degrees Celsius, it reduced the read latency by 30%. But it's not as effective at 85 degrees Celsius, 25%, because of the variation across the DIMMs. If you do this DIVA profiling, we find out that you can actually reduce the read latency by about 35%, more than AL-DRAM, at both temperatures. Because here, we're not really relying on the temperature. We're really exploiting that variation, spatial variation. And there's some more ideas in the paper that looks at, oh, you know where these errors happen, so actually you change the ECC, error correcting codes mechanism, to cover for these errors better, and that improves your read latency. And these are the write latencies. The results are very similar. You can reduce the write latencies more than adaptive latency DRAM. And this way, I think you can adapt to aging, wear-out related issues, because you're determining your latency dynamically online. That's something we cannot easily test. But of course, you need to use ECC. Yes.
Let's say you do profile and dynamically choose the latency. Since you're dynamically choosing it, you need some kind of process, some kind of hardware or software to do this choosing. Won't the delay that it adds would be larger than what you're saving? Because you require some computation, some maybe read from memory to know this line requires this kind of latency.
Yeah, I think you can do it off the side. Certainly, there's an overhead to the profiling, but you don't need to choose the latency and then schedule. Basically, you schedule with some latency, and on the side, you can do computation to figure out what your latency should be. And once you figure that out, you use that for the remaining accesses.
But again, once you choose that, you need to, it's information. It's stored somewhere, or shouldn't it add a delay since you have this ability to choose?
So I don't think it would add a delay on the critical path, but it adds complexity, certainly, on the side. No question about that. But I don't think it's a good idea to design the controller to add a delay. These things are basically all optional, in a sense. You don't need to add it to your critical path. Okay. Okay, so advanced and disadvantages. This is, I think, the big plus here is you can automatically find the lowest reliable operating latency at system runtime. And here we're doing it for the entire DRAM chip, not for different regions. Hopefully, this is lower production time testing cost. and it reduces latency more than prior methods. The caveat is it's relying on ECC. And when you rely on ECC, you can, of course, play a lot more tricks. And it reduces latency at high temperatures as well. The disadvantage is it requires knowledge of this inherently slow regions. As I said, I think the interface between the memory controller and memory should change. If the device provides a lot more information to the memory controller, then you can do a lot more. And it requires ECC, obviously. That's a disadvantage. But I think going forward, we will need more ECC in DRAM. And it imposes overhead during runtime profiling, certainly. Yes?
I think the reliance on ECC here needs to be studied very carefully. The reason is that you may have an effect where things suddenly go bad.
Yes.
It's not smooth degradation. Then you go from no errors to too many errors very easily.
Yeah, yeah.
So you can't really use ECC.
Yeah, I agree with you. So what we're doing with ECC over here is the big reliance in terms of reducing latency is this inherently slow region. And we add a margin on top of that. But yes, if you have too many errors in the bit lines, for example, that are randomly distributed, you may actually not be able to correct them. I absolutely agree with you.
Yeah, no, what I'm saying is that the phenomenon, the dependence of error rate on, let's say, latency,
Mhm.
may be a sharp dependence. So it's not as if you reduce latency a bit and suddenly one error.
I see, yeah, yeah.
It goes from excellent to terrible.
Yeah, yeah.
Because there is correlation among the cells. They're not going to be random.
Sure. So according to what we see, yes, I think that needs to be studied more, similar to the curves that I've shown for refresh, right? You have the refresh interval and then your probability. Yeah, I agree. There needs to be more rigorous studies to be done over there. That's a very good point. Any other questions? Yes.
Here you introduced a lot of heterogeneity in the operation of the system, of like different processes. And even yesterday, when you talked about PIM, when you said deciding online whether to send it to the PIM processor or do it in the CPU, you introduce a lot of heterogeneity, which is a side channel, and it's actually opposing, which is a side channel, and you can use that to exploit processes and to introduce some security problems.
I didn't understand where the side channel is coming from.
If you like in this situation, if you use a slow memory region, slow column,
Yeah.
you'll have a longer read. Or
Oh, I see, I see. And
in the PIM situation, if you somehow manage to make the CPU send more instruction to the PIM, or do it inside the CPU, it have different characteristics. You produce side channels.
sure, I mean, any time you have some sort of measurable latency variation and someone can time it, you have a timing side channel. I agree with that.
And that's actually a bit contradicting to the security part of your lecture.
I see.
Designers should be aware of this interesting, of this characteristic
Yeah.
because it's not apparent to the programmer.
Yeah.
Even about security that way.
Yeah, I mean, I wasn't thinking of timing side channels when I said that, but maybe yes. I don't know. I think timing side channels are a very hairy issue that people need to somehow fix. If we get rid of, it's very hard to get rid of the timing heterogeneity in the systems that we have today, in my opinion. But I agree that this is going to make things a lot more heterogeneous in terms of timing. And if somebody can measure that, and if somebody can make sense out of it, which they could potentially, in a systematic way, that could open up yet another timing channel vulnerability, yes. But my feeling is that needs to be solved at some other level. Somehow we would like to be able to do all of this internally without exposing any of those channels outside. I think that's the thing that people are researching right now. How do you do that?
Can be measured somehow. So you cannot say you want this latency and you want to know the exception. When there is an exception, you will feel it. It's the same like
Yeah.
caches. So
Exactly. It's the same like cache. Exactly.
it's
Yeah.
there. I'm not sure.
Yeah. So I'm not sure if this is making it really worse because it already exists everywhere.
Avi, you have something to comment on that?
That's true. Probably somebody. Okay. Any other questions
No, but
on this?
seriously, this is something that sometimes you will have to address it because in general, whenever you are doing optimization in terms of timing, you expose yourself to
Yeah, I agree with that, but that doesn't mean that we shouldn't do optimizations in terms of timing. So somehow, my feeling is that that issue needs to be resolved at some other layer, in the sense that we'll need to come up with a. I don't think we can. At least we know how to reason about timing tight channels today.
Okay, now we are in the retro that you mentioned. Let's
Okay, there you go. Thank you. I'm the rat, and you're escaping me from the hole now. Thank you. Okay. Yeah, I mean, we could have a philosophical discussion about timing side channels a lot. Okay. So let's continue a little bit more, and then we'll take a break, maybe. Or should we take a break now? What do people think? Now, okay, let's take a 10-minute break. Yeah, this is probably a good time. Let's take a 10-minute break and come back at 15 past.